Let's do one last example. So in this example, the flow velocity is given by u equals some constant q times x divided by r squared, and v equal q times y divided by r squared, where in this case r squared actually has x and y built into it, right? So r squared equals x squared plus y squared, and again we can assume that that constant q is, a positive number for the sake of argument. So using the usual approach, basically we use, our definition for a streamline, dx over u equal dy over v. Plug in u and v. In this case, we'll see that, let's see, the q's cancel, the r's cancel, and we're left with something that looks like dx over x equals dy over y. Using the same approach from the previous problems, we'll integrate from some initial point x0 and y0 to some future location on the streamline x and y. And again, dx over x integrated gives you natural log of x over x0, and the right-hand side is natural log of y over y0. So far, the only difference between the previous problem is that there's no minus sign in front of the right-hand side here. We exponentiate both sides. And that'll release, a right hand, it'll, make it so that 1 equals y times x0 over y0 times x. And we can solve that to make that look more normal. So you can solve that and realize that it's actually the equation of a line. Y equals y0 over x0 times x. So the prefactor y0 over x0 is a constant. It basically defines the slope of the line. So this is a family of lines that goes through the origin. There's no offset. And it has basically arbitrary slope that depends on where the starting point x0 and y0 is. And of course, we go back to the task of which direction does the fluid flow here. And if you look, there's a couple different ways you can do this, but if you look at the horizontal velocity u, at any positive value of x, it moves to the right because it's u would be a positive number. And for any negative value of x, the horizontal component would be to the left. So u would be a negative number. And so you can work out the arrows that go with each one of these. So that particular flow pattern is called a source flow because it's as if there's a point right at the center where you have like a nozzle that you are releasing fluid that sort of flows outward away radially from the point source. So we'll see uses for that later in the course when we're doing modeling, but that's what this is. This is called a source flow. This is a more natural flow to describe in radial coordinates. So if we had been doing this in radial coordinates, the velocity profile would have been given by v sub r equals q over r, so much easier to describe, and v theta equals 0. In that case, we could also go through the math and see that dr over vr equals, r d theta over v theta. It's never convenient to do it that way because v theta in this case is 0, so it's better to multiply both sides of the equation by their denominators. And after you do that, you can see that d theta is equal to 0, meaning that if I were to do any integration, I would get things that look like theta equal a constant that depends on the initial value of theta or whatever it is. So you'll find, theta equals a constant. Well, what is that? Theta equals a constant is just the description of a line that radiates out from the center, in a straight line. So that's exactly the same solution that we got when we were in Cartesian coordinates. So it's not really any harder to do these kind of calculations in radial coordinates as long as the velocity profiles are given to you that way.